Alright, so our first unit of the year is going to be on math, units, and factor dimensional analysis, or F.D.A. And our first lesson on that is going to be on math number 1. We're going to cover three topics in this lesson. The first one is going to be on scientific units, the next on scientific notation, and the third and last topic will be on significant figures. On units, there are multiple systems of units that are out there, different ways of measuring things. Say, for example, for height, you could talk about your height in feet, or you could talk about it in meters. The first one, feet, would be an example of something in the U.S. customary system. This is the set of units that most Americans use on an everyday basis. Things like miles or feet for distance, inches. You talk about how many pounds you weigh. You could talk about a gallon of milk or a quart of this or something like that. Typically these are U.S. customary units that we'd be talking about there. In science, though, typically we tend to use a system that's different, one that is a little bit easier to use because of the fact that its units all go into each other by factors of 10. As you know, there are 12 inches in a foot, but 3 feet in a yard, 16.5 feet in a rod, and all sorts of weird types of units that get out there. But metric system units, which is the sort of everyday term for our international system that we'll talk about in a second, is the metric system. These types of units always are factors of 10 into each other, so 10 or 100 or 1,000 or something like that. So we're going to use in this class and in all science classes the International System of Units, the SI system, so-called because of the French wording of International System of Units. Is why it's SI and not IS. So these would be things like, as are on the table below, that the unit of length is in meters, the volume in liters, time is seconds, that one you're fairly familiar with. Mass is in grams, temperature would be Kelvin, or Celsius is another one we'll use in this class. Energy in joules. There are other ones, like Newton is a unit of force. But these are certain common base units you see in the SI system. So if you want to talk about how tall someone is, you would say they're so many meters tall, or how much time has passed, it's been so many seconds, and so on and so forth. So these are the ones that you'd use. One of the problems you run into with these types of units, though, is that, okay, you can describe yourself as being 1.9 meters tall. That's fine. But what if you want to describe the size of a flea? A meter is much too large. I mean, it's a little over 3 feet. You wouldn't want to describe a flea as being 0.000034 meters or whatever. That would be very unwieldy. We need a better set of units. Similarly, it's over a billion, actually it's over 100 billion meters to the sun from the Earth on average. You wouldn't want to describe that in terms of meters. You'd instead want a different set of units that would allow you to figure this out and allow you to make these units in much more easy to use forms. And so to do that, the metric system, or the SI system, uses a series of prefixes added to these units. The SI prefixes, the smaller ones and larger ones, are both listed here. They typically work as I'm about to show you, is that if you talk about, say, something very small, like our flea, is that if we were going to measure him, we would want something that's a much smaller unit. An example of this might be something like, say, we might measure him in micrometers. And so the reason why we know this would be because we'd say, well, okay, a flea is how much smaller than a meter? You'd say, well, a flea is going to be, less than, well, under 1,000th of a meter, but larger than 1,000,000th of a meter. So we say, well, 1,000th would be what power of 10? Well, 1,000th would be 10 to the negative third. 1,000,000th would be 10 to the negative sixth. Since the flea would fit somewhere in between these, we would use the unit that's sort of in between each of those. And so as a result, that we are going to go ahead and we would say he'd be measured in micrometers is the way you do it. Similarly, if we were going to talk, say, about the distance between the Earth and the Sun, we said that's over 100 billion meters. And so a billion is 10 to the 9th power. So we look for our value for 10 to the 9th, and we say, oh, there's 10 to the 9th right there. And so we would measure that in gigameters. So we'd say it's going to be so many gigameters away from the Earth to the Sun. And so this is basically how our SI units work, how our prefixes work. You add the prefix onto the unit in order to create a unit which is larger or smaller than the one that you had originally so that you can have one that fits what you're measuring a whole lot better. So let's take a look at some examples on this. So first question, how many meters are in 1 centimeter? Well, let's break this down. To do this, we want to say, all right, what's the prefix? The prefix is centi. And since the prefix is centi, what does centi mean? Well, if you look it up on there, you'll see centi means 10 to the negative second. And so 10 to the negative second. So that would mean that what we can do, if we want to figure this out, is we're basically going to do a substitution. We would say 1, but instead of centi in there, we'll put in the number, 10 to the negative second meters. Okay? 1 centimeter is 1 10 to the negative second meters. 1 times 10 to the negative second, well, that's just 0.01 meters. So 1 centimeter is equal to 0.01 meters. 5.4 gigameters. All right, what's the prefix? The prefix is giga. What does giga mean? Giga means 10 to the 9th. And so to do this, we would say that 5.4 gigameters would be 5.4 times 10 to the 9th meters. Because we have 5.4, then we have 10 to the 9th, then we have meters, just like that. And so 5.4 gigameters is 5.4 times 10 to the 9th meters. Okay, 76, what is that? Well, this right here, this mu, stands for micro. And it is the little U-shaped thing. It's called a mu. It's the Greek letter mu. It's their equivalent for an M. And so that basically said that is the symbol for micro. And so we'd say that's the prefix right there is micro. What does micro mean? Micro means 10 to the negative 6th. And so to write this out, we'd say this is going to be equal to 76 times 10 to the negative 6th meters, like that. And so 76 micrometers would be, we'd have to say 0.1234576 meters. So 76 micrometers would be that value right there. So this is how you go about converting between different units for that. Okay, next topic is going to be on scientific notation. Scientific notation, the general form of that is going to be a times 10 to the b power. But why would we want to use this? What would be the point of doing this? On our previous problem, you notice we had several things that had all sorts of zeros on them. Made it very unwieldy to write down. Something like our last one where we had to have 6 zeros or 7, however many zeros we had there, 5 zeros, before we got to some non-zero digits. A lot of numbers in science are either extremely large or extremely small, and as a result you're going to end up writing out all sorts of zeros unless you use something like scientific notation to condense it. For scientific notation, there are a couple parts. The general form is a times 10 to the b power. The first one here, the coefficient out front, that's a. It has a value which is always between 1 and 10. So it is always between 1 and 10. So it can't ever be anything that's smaller than 1. You couldn't have a number out front that was 0.8 or 0.6. And it can't ever be larger than, it can't be 10 or larger. It couldn't even be 10. It could be 9.99999 because that number's smaller than 10, but it couldn't be 10. It couldn't be 10.1. Couldn't be 33. It always has to be something that falls with one digit, then a decimal point, and then maybe some digits afterwards. The next part is going to be the coefficient. That's b right out here. Is this number could be anything, basically any value as long as it's a whole number. So b has to be a whole number. You're not going to have something like 3.4 times 10 to the 7.6. You could have 3.4 times 10 to the 7th, or 3.4 times 10 to the negative 7th, but or 7, or even 10 to the 76th. But you would never have 10 to the 7.6. Below, we'll see some examples. You see our standard form over there on the left. I have 13.4 for the first one. Now, in this case right here, the first question you'd want to ask is, look at what's on the left side of the decimal. Is it between 1 and 10? It's 13 right now, so it's not. We're going to have to convert this. Where do we have to move the decimal to get it? so that the first digit, it's one digit, then a decimal. Well, it looks like we have to move it over one spot. And since we have to move it over one spot, that means that we're going to have something that's 10 to the first power. And so we shift this over, and you see on the right, 1.34 times 10 to the first power, because we shift over one spot. For our next one here, 450,000, well, where do we put the decimal? Well, let's put the decimal right there. How many spots did it have to shift over? There's go 1, 2, 3, 4, 5 spots. And so this is going to be 4.5 times 10 to the fifth, because it's shifted over 5 spots. First two we've done here have both been numbers that have been larger than 1. This next one, 0.00991, is smaller than 1. Since the number is smaller than 1, it means that the exponent of 10, the power it's raised to, has to be a negative number. It's going to be a negative exponent. And so in this case, if we wanted to have one non-zero digit first, the decimal place is going to have to move to right there. And so how many spots do we have to move it over? We have to go over 1, 2, 3 spots. But since it's less than 1, it's going to be 10 to the negative third right there. And so that's what we've got there. So it's going to be 9.91 times 10 to the negative third. Our next one, also smaller than 1, so we'll have a negative exponent. How many spots do we have to move over? We have to go over 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. So this would be 3 times 10 to the negative ninth. Similarly, on our last one, we have 2.34. How many spots do we have to move it over to make this number between 1 and 10? Well, we've actually already got it between 1 and 10. It's 2.34. So this is one where writing it in scientific notation may not be very helpful, because it really makes the number a lot larger. But if you have to write in scientific notation, you do it like this. You have 2.34 times 10 to the 0 power, because 10 to the 0 power is 1. 2.34 times 1 is just 2.34. And so that's basically what we've got for our scientific notation and how to write that out. So on our next one here, let's try a couple examples. So convert the following in or out of scientific notation. So the first one here is 780. This is a conventional form, so we're going to take it to scientific notation. So 780, we know we have to get it to the point where we have 7.8 something. And so how many spots do we have to move the decimal here? How many spots do we move it over? We go 1, 2 spots. It is certainly the case that this number is larger than 1, so it's positive. So 10 to the second. 7.8 times 10 to the second what we have for this one. On our next one, the number is smaller than 1. We know we're going to have a negative exponent. We have to move the decimal place over how many spots? 1, 2, 3, 4 spots. So we'd say 2.34 times 10 to the negative fourth, because we had to move it over 4 spots and it's smaller than 1. Our next one, 7.98 times 10 to the negative fourth, is already in scientific notation, so we have to take it out of scientific notation. And so in this case, it is negative fourth, which means it's smaller than 1. So we're going to start off here by 0. How many spots move it over? 1, 2, 3, 4. That'll be where the 7 is. And then we have to add the 9, 8 on the end. So 0.000798 is what we get for that one. Our last one, 9.8 times 10 to the 14th. This is definitely larger than 1. This is it's got a positive exponent. It's larger than 1. It's a very large positive exponent, so we're going to write off all sorts of zeros here. So we'd say this one is 9, 8, and then we have to move, that's the first one right there is the 8. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Add our commas here so we can see how big this number is. And that gives us, see, hundreds, thousands, millions, billions, trillions. 980 trillion would be how you'd say that number right out there. So this is scientific notation. This is how you would use this. All right. Our last topic for today is going to be on significant figures. And so in order to discuss this, let's start off with sort of a general question. That question is, how far is it to the interstate? Well, if you think about it, and this is from the school is about a mile from the interstate. And so if someone drives up and says, hey, how far do I have to drive to get to the interstate? You'd say a mile. What would happen then if you were to back up an inch? Doop. He says, how far am I from the interstate now? You'd still say a mile. You wouldn't say a mile and an inch. Why not? Well, because when you gave the distance, you gave it in miles to the nearest mile. You were only measuring it to the nearest mile there. You didn't measure it any more precise. If you said that, oh, it's a mile and an inch now, that would mean that you knew that before that he was exactly 1 mile to the nearest inch. And now, he's just an inch more than that. So this is an example of somewhere where we have to be very careful with how we describe our measurements. Similarly, is if we tried to use a very large unit, like say gigameters, you know, 1 billion meters. If I said, how many gigameters is it to the interstate? Well, near-wise, it'd be 0 to the nearest gigameter. So I'm already at the interstate? No, not at all. It's just that if you're not careful about how you round things, then you can basically give inaccurate data. The term for this, the technical term for this, is called precision. And whenever you measure something, you always need to indicate how much precision you had. If you don't, then what can end up happening is you can say, I measured this out, and I measured this to be, 30 centimeters. Well, 30 centimeters could tell me that you measured this all the way out to 30.000 centimeters. You measure this already out to the thousandths place, and it's exactly 30 centimeters. Or it could mean you were just sort of lazy and said, it's close to 30 centimeters, and because it was like 27.4 or whatever. But you said it's close to 30, I'll call it 30. Is that if then someone says, I'm going to add something that's a centimeter to this, if you were just rounding to the nearest tens of centimeters, then adding exactly a centimeter to it, someone's going to think it's 31. Is it actually 31? Maybe not. I mean, it could be anything from 26 to 35 if you don't tell them exactly how far that you measured in the first place. So segment figures describe the precision of measurement, how precisely you measured something. Now, if you see a number that's been written down that's already been put into significant figures, sometimes we have to figure out exactly how many significant figures does that number have, so that when we do calculation with it, which we'll do later, that we're able to actually measure things and do those calculations correctly. So the first rule for significant figures is that all non-zero digits are significant. Okay? So let's take a look at how this would work. Let's suppose that we had a number, that it was something like this. It was 709. So this is our number here. We want to figure out how many significant figures does this number have. First rule is this. All non-zeros are significant. Is the 7 a non-zero digit? Yes, so it is significant. Is the 9 a non-zero digit? Yes, so it's significant. So we know that this has at least 2 significant figures here. Next rule. Zeros between non-zero digits are significant. Is the 0 in 709 between 2 non-zero digits? Yes, it is. So it's significant. So this one right here has 3 significant figures. So we can know that right there. Alright? So that's what we've got here. What if there's zeros not between non-zero digits? These are our next 2 rules here. So let's see what we've got for them. So the first rule that we have, this is the third rule, zeros on the far left, leading zeros are never significant. Never significant. That's just an overall rule. Can't get around that. So if our number was something like 050, we have 50 we're going to write it out this way, is we know that the 5 is significant because of the fact that it is a non-zero digit. The first 0 is not significant because it's a leading 0. It's on the far left. It's never significant. So that one's like, nope, not significant here. What about that last 0? Well, this is where we go to rule 4. Zeros that are on the far right of a number, that is trailing zeros, are only significant if they are to the right of the decimal. And so, where's the decimal here? Well, the decimal should be right there. And so, because of the fact that that 0 is to the left of the decimal, it's not significant. This number only has 1 significant figure. Okay? Now, what if instead this had been this number? 050.00. Well, let's take a look. The 5 is significant because it's not 0. Are there any zeros that are trailing zeros that are to the right of the decimal? Yes. There's one out here and one right here. But since the 5 and this 0 are significant, any zeros in between them have to be significant too. So this one is also significant, and this would have 4 significant figures, just like that. So, so that's one way of remembering this right here. Let's try some of these out right after the ding. All right. So, question here, how many significant figures are in the following? So our first one is 504. Well, let's take a look. The first rule is the non-zero digits are significant. So we have at least 2. We have a 0, but it's in between. Since it's in between, then it means that that one is significant, and this one has 3. Our next one, non-zero digits are significant. The 8 is significant. The 9 is significant. What about the zeros in the front? Well, they're leading zeros. Leading zeros are never significant. So this would only have 2. Our next one, 9,100. We know the 9 is significant. We know the 1 is significant. What about the last 2 zeros? Trailing zeros are sometimes significant, but only if they are to the right of the decimal point. These are to the left of the decimal point, so they're not significant. We have 2 significant figures. For our next one, 68.30, we know that the 6 is significant. We know the 8 is significant. We know the 3 is significant because they're all not zeros. The last 0 is a trailing 0. Is he to the right of the decimal? Yes, he is. So is he significant? Yes, he is. So this one right here has 4 significant figures. Our last one right here, we know the 4 is significant and the 1 is significant. Those 3 zeros at the front are leading zeros, so they are not significant. The 0 that's on the back is a trailing 0, and he is to the right of the decimal, so he is significant, and so this has 3 significant figures. And so that's how we'd figure that out right there. So let's take a look at our next guy here. Come on. So, round the following to 2 significant figures. So we've got numbers that are not the right number of significant figures. And so we want to get them there. So our first one here is 8,321. If we want this number to round to something that only has 2, it's basically going to be the leading significant figures. The first number that is significant will be the ones we're going to start with, which in this case is going to be the 8 and the 3. And so those are going to be the 2 we're going to start with. So we know we have 8, 3. The problem is if we said 83 is our answer, that does have 2 significant figures. 8,321 does not round to 83. It would, however, round to 8,300. And so this would be the correct way of writing this, because this does have 2 significant figures, 8,300, because of the fact that the 2 trailing zeros are to the left of the decimal and so aren't significant. So 8,300 is what we have for that. Our next one, let's find the first digits that are significant, and those are going to be the 4 and the 5. So those are going to be the 2 that we're going to be interested in, are going to be our significant figures. And so because of the fact that this is going to be, let's see, so we have 0.045, right? Well, let's take a look. That has 2 significant figures, but look at the digit that is after that. Look at the 6. If you look at the 6 there, then you'll see that's going to make the 5 want to do what? Round up. If the 5 rounds up, then we'll have to change that. So it's not going to be 0.45, it's going to be 0.46. And so this has 2 significant figures. This is what 0.045672 would round to. Our next one, scientific notation. So to do scientific notation, this is easy. There's no leading zeros here. The first 2 digits that are significant are the 7 and the 6. And so this is just 7.6 times 10 to the 8th. And that's it right there. Just 7.6 times 10 to the 8th. Fairly straightforward here. Our last one. Let's take a look at this. First 2 significant digits are 7 and 9. But what's the one that's after the 9? Well, that's going to be a 9. And the 9 is going to round up. And if the 9 rounds up, then that's going to force this to turn into not 790,000, but rather turn into 800,000. What's the problem with 800,000? How many significant figures does it have? It only has 1. We were asked to round it to 2. Now, there are 2 ways to go about doing this. One is to write it out as 800,000. that is an acceptable answer. You can never write something with more significant figures than what it has, but it is acceptable to write it with less if there's no other choice. And so this is one way of writing a correct answer. It doesn't tell you, though, the correct number of significant figures. It's close as you can get it. It is acceptable sometimes, but it's not ideal. If you want to make sure you get this exactly right, the way to do it is to convert it into scientific notation. If you convert scientific notation, then this simply becomes 8.0 times 10 to the, let's count the decimal spots over. We have to go over 1, 2, 3, 4, 5. So 10 to the 5th. So that right there, 8.0 times 10 to the 5th, has how many significant figures? 2. And so as such, that's going to be your answer right there. So this has been our first discussion here, and so we will go on to new ones next time.